Hello viewers, in today's class we are going to discuss yet another important and very conceptual problem from integrals using the concept of beta and gamma functions. Right, so here again we have a very nice integral which can be easily solved by using the concept of beta function and gamma function. Right, so let us start. So let us take this integral as I, and here we are going to make use of the substitution method, right? So here we'll take this quantity, that is x square is equal to t, right? So x is equal to square root of t. Let us differentiate x with respect to t. So dx over dt is the derivative of square root of t, which is 1 over 2 times square root of t. So dx can now be written as dt over 2 times square root of t, right? Okay, now see here the limits of integration vary from 0 to infinity. So when x is equal to 0, then the value of t can be obtained from this expression. So t is also equal to 0. And when x is tending to infinity, then t also tends to infinity, right? So now we can write this integral in terms of our new variable t. So we can now write I as 0 to infinity x raised to 1 by 3. Now see here x is equal to square root of t, which is t raised to half. So here we can write t raised to half raised to 1 by 3, right? And in the denominator we have 1 plus t, and for dx we can now write dt over 2 times t raised to half, right? So let us rearrange the terms. Now we can take half outside the integral. So we have half 0 to infinity t raised to, this is 1 over 6, and taking this half to the numerator we have here minus half, and then we have 1 plus t dt. So now we can write half 0 to infinity, and if we subtract 1 by 6 and half, we'll get minus 1 over 3, right? And here we have 1 plus t raised to 1, right? So now at this step, let us apply the beta function, right? Now see, the beta function is defined as beta mn is given by the integral, that is 0 to infinity x raised to m minus 1 divided by 1 plus x raised to m plus n, and here we have dx, right? So now our aim is to express this quantity like this, right? So here the variable is x and here the variable is t. Now the variable is not going to make any difference because this in definite integrals this is a dummy variable. So here we have t raised to minus 1 by 3, right? And here we have x raised to m minus 1. So if we write m minus 1 is equal to minus 1 by 3, and here we have 1 plus t raised to 1. Here we have 1 plus x raised to m plus n. So m plus n may be taken as 1, right? So now we have two equations. We can find out the values of m and n from these two equations. So we have minus 1 by 3 plus 1, solving this one. So this is simply 2 by 3. Taking m is equal to 2 by 3 in this equation, we have 2 by 3 plus n is equal to 1. So n is 1 minus 2 by 3, that is equal to 1 by 3. So now this integral I takes the form, that is half 0 to infinity t raised to minus 1 by 3. Now see, minus 1 by 3 can be written as m minus 1. So m is 2 by 3. So we can write 2 by 3 minus 1. And here we have 1 plus t raised to 1. 1 is equal to m plus n. M is 2 by 3 plus 1 by 3, right? And here we have dt. So the sole objective is to express this quantity like this, which we have done in this way, right? So now what we will do, we'll write half, and now this integral is equal to beta m comma n, right? M is 2 by 3, n is 1 by 3. So we have beta, this is 2 by 3, and here we have 1 by 3. So now to calculate the value of beta 2 by 3 comma 1 by 3, we'll make use of another important relation, that is beta mn is given by gamma m, then we have gamma of n divided by gamma of m plus n, right? So this is half gamma of 2 by 3, m is 2 by 3, n is 1 by 3, gamma is gamma 1 over 3, then we have gamma of 2 by 3 plus 1 by 3, right? So this is 2 by 3. Now 2 by 3 plus 1 by 3 is equal to 1. So we have gamma of 1. Gamma of 1 is simply 1. So I is now equal to half gamma of 2 by 3. 2 by 3 can be written as 1 minus 1 by 3. 3 ones are 3. 3 minus 1, 2. So 2 by 3 gamma of 1 by 3. And in the denominator we have 1, right? So now we have the value of I like this, right? Now here again we'll make use of another important result from beta gamma functions. So now we know that the Euler's reflection formula, that is gamma of 1 minus n, gamma of n is equal to pi divided by sine of n pi, right? So this is the well-known Euler's reflection formula in beta gamma functions. So if we compare this side with this one, then n is equal to 1 by 3. So here we have 1 by 3, here we have 1 by 3. So the value of this expression is pi divided by sine n pi. So n is our 1 by 3. So here we have pi over 3. This is n pi, right? So this is half pi. Sine pi by 3 is sine 60. Sine 60 is root 3 over 2, right? So this 2 and this 2 get cancelled. So we are left with pi over square root of 3, right? So here's the value of this integral is given by pi divided by square root of 3. And moreover, this integral can also be solved by using the method of residues, that is the Cauchy's residue theorem. Hello viewers, in today's class we are going to discuss yet another important and very conceptual problem from integrals, right? So here in this lecture we'll again solve a very nice integral which is 0 to infinity, and we have dx over x cube plus 1, right? So this is a very important integral which appears in calculus of residues, and we can also solve this integral by the method of using the Cauchy's residue theorem. But in this series we are focusing on the application of beta and gamma functions, right? So we'll solve this integral by using the concept of beta and gamma functions, right? We'll also solve these all type of integrals using the calculus of residues in our next series, right? So let us take this integral as I, right? So again we'll take help of the method of substitution. So here we'll make this substitution, that is let x cube is equal to t, right? So x can be written as t raised to 1 by 3. So differentiating both sides with respect to t, we have dx over dt is equal to 1 by 3 t raised to 1 by 3 minus 1. Using the power rule for differentiation, 1 by 3 t raised to minus 2 by 3, right? So dx can now be written as 1 by 3 t raised to minus this is 2 by 3, and here we have dt, right? Now see, the limits vary from 0 to infinity. So when x is 0, we can take the value of t from this relation. So t is also 0, and here when x tends to infinity, then t also goes to infinity, right? So now this integral I can be written in terms of t as 0 to infinity. For dx, we can write 1 by 3 t raised to minus 2 by 3 dt divided by x cube plus 1. X cube is t, so we have t plus 1, right? So let us rearrange the terms. So we have 1 over 3, 0 to infinity, t raised to minus 2 by 3, and here we can write 1 plus t, writing t plus 1 as 1 plus t raised to 1, right? So now we'll convert this integral into the beta function. So now see, we can rewrite this integral as 1 over 3, 0 to infinity. Now t raised to minus 2 by 3 can be written as 1 over 3 minus 1, right? So we have already explained this method in our earlier videos, how to write this exponent and this exponent, right? So we have t raised to minus 2 by 3 as 1 by 3 minus 1. Here we have dt, and 1 plus t raised to 1 can be written as 1 by 3 plus 2 by 3, right? So because 2 plus 1 3, 3 over 3 is 1, so we'll get the same integral. So the purpose of writing this integral like this is the beta function, because beta function is responsible for writing this integral in this form, right? Because beta function is defined like this: 0 to infinity, x raised to m minus 1, 1 plus x raised to m plus n dx, right? So the value of m is obviously 1 over 3, and the value of n is equal to 2 by 3, right? So now this integral is equal to 1 by 3 beta of 1 by 3 and 2 by 3, right? So let us make use of another important relation in beta gamma function, that is beta mn is equal to gamma of m, gamma of n divided by gamma of m plus n. So here we have 1 over 3, gamma of 1 over 3, gamma of 2 by 3, and then we have gamma of 1 by 3 plus 2 by 3, right? Now see, this term is 1 by 3 plus 2 by 3, that is equal to gamma of 1. Gamma of 1 is equal to 1. So this expression is now equal to 1 by 3. We have gamma of 1 by 3 and gamma of 2 by 3. So gamma of 2 by 3 can also be written as 1 minus 1 over 3, right? So the purpose of writing gamma 2 by 3 like this, gamma 1 minus 1 by 3, because this expression can be written like this, that is gamma of n, gamma of 1 minus n is equal to pi over sine n pi, right? So this is the famous Euler's reflection formula in beta gamma functions. So here n is 1 by 3, right? So here we have gamma 1 by 3, gamma 1 minus 1 by 3. So this expression is now pi over sine, that is pi over sine n pi. So n is 1 by 3. So here we have pi by 3. So now we have 1 over 3 pi. Sine pi by 3 is sine 60 degrees. That is a square root of 3 over 2, right? So now the value of this integral I can be written as 2 pi. This 2 goes to the numerator. So we have 2 pi over 3 root 3, right? So viewers, the value of this integral is equal to 2 pi divided by 3 times the square root of 3. So this is how, by the application of beta and gamma functions, we can solve these kind of integrals.